Hello friends. So today we are going to discuss the questions from the year 2014 and total of 6 questions, and it will be a combination of both mains as well as advanced. So first question, it was asked in 2014 mains, and it states that a green light is incident from the water to the air water interface at the critical angle theta. Select the correct statement. So based on this criticality angle of the green light, we have to find out which of the, you can say, lights as compared to green will be able to come out to the air medium. That is the basic. So here we can just draw an approximate figure for that. Suppose this is the, and we have air as well as water, and we have a green light that is incident at angle critical, that is given as theta. Okay, so this is our green light, and let us suppose, yeah, that will be sufficient. So here this angle of refraction will be equal to 90 degree. So if we can say that at critical angle the light refracts along the boundary, that is making the angle of 90 degree with the normal. At critical angle you can say that light refracts along the boundary or we can say that it emerges at 90 degree to the normal. Okay. So total internal reflection will takes place if the angle of incident must be greater than the critical angle. Okay, say total internal reflections takes place, and this is the angle of incidence is greater than critical angle. Okay. And this critical angle is, you can say, frequency dependent, because the refractive index itself is dependent upon the wavelength or frequency. You can say that critical angle depends upon frequency, and this frequency is, you can say that frequency is dependent upon frequency or wavelength. It is dependent upon the refractive index. And if we see the relationship between the wavelength and refractive index, we can write that refractive index decreases with increasing wavelength. So refractive index decreases with increasing wavelength. Increasing wavelength, or we can say lower frequency. Lower frequency. And the red light is, so because of this we can say that red light has lower refractive index than green, and the blue violet light has a higher index. Blue and violet light has higher refractive index. Okay. So now the green light is at a critical angle. So based on this we can make a comparison that a light with lower frequency, that is our red, orange, etc., and will have smaller refractive index, thus larger critical angle, and they are going to refract and escape this incident angle. Okay. So we can say that the spectrum of light whose frequency is less than green light will come out to the air medium. Green light will come out to the air medium. So therefore we can say the option number B is the correct one. Option B is correct. So we come to the next question, and here it was asked in the 2014 advance, and it states that a point source S is placed at the bottom of the transparent block of height 10 mm and refractive index 2.72. It is immersed in the lower refractive index liquid as shown in the figure. It is found that the light emerging from the block to the liquid forms a circular bright spot of diameter 11.54 mm on the top of the block. The refractive index of the liquid is. So we are given the source, and it is said that a circular bright spot is formed at the top of the liquid. So we can just something like this, and the ray of light will be forming like this. So we can assume that let this angle be theta, and we are given its diameter, that is 11.54, and we are given that the height is 10 mm. So this height is our 10 mm. So it means we can just draw a conclusion from here that the light which is not making a bright spot will be actually suffering the total internal reflection. Okay. So it means the light which is beyond this portion is going to suffer total internal reflection. Therefore, we can just write a formula for total internal reflection. So we can say the bright spot on the top corresponds to, on the top face, corresponds to a ray emerging from the point source. A ray emerging from point source and reaching the top just before total internal reflection. So it means that the rays that emerge through the bright spot do so at an angle which will be less than or equal to the critical angle. So you can say the rays that emerge do so at angles less than or equal to critical angle. And let us call this critical angle as C. Therefore, we can write that our sine of critical angle will be equal to n2 upon n1. And for maximum angle of incidence, that will be corresponding to the ray that travels from the point of source to the edge of the bright circle. So we can say this will be our maximum angle of incidence to the normal, this angle. You can say that the maximum angle of incidence corresponds to the ray that travels from point source to the edge of the bright circle, to the edge of bright circle. So therefore, we can write that our tangent of theta, tangent of C will be equal to our R upon H. Okay, radius we already know, height is also given to us. Rather, we can say we know the diameter, so we are going to get this as 11.54 divided by 2, and height is given to us as 10. So this comes as 0.577. So we can find out a critical angle at our C will be equal to tangent inverse of 0.577, and this approximately is equal to 30 degree. Now we can use the Snell's law at critical angle. Snell's law at critical angle. So we can say our sine of C will be equal to n2 upon n1. n2 we need to find out. n1 is our 2.72. So this gives us that our n2 will be equal to 2.72, and sine of 30, that is our 1 by 2. So this gives us that our n2 will be approximately equal to 1.36. So the option 1.36, option number C, is the correct one. Option C is correct. Next question. It was asked in the 2014 mains, and it states that a thin convex lens made from crown glass mu is 3 by 2 has a focal length f. When it is measured in two different liquids having refractive indexes 4 by 3 and 5 by 3, it has focal lengths f1 and f2 respectively. The correct relation between the focal length is. So we are going to find out what will be the relation of the focal length with respect to two different liquids, that is two different refractive indexes. And we can make use of the formula, which is our standard formula, and that standard formula for a thin glass, it is given as, for thin lens we can write that f upon the focal length in medium is equal to refractive index of lens divided by refractive index of the medium minus 1, and here comes as 1 upon R1 minus 1 upon R2. And here we have, you can say, three different refractive indexes. First is refractive index of the crown glass. We can say we are given that mu for the lens, it is given as 3 by 2, and we have two mediums. Let us suppose we call as mu1, that is our 4 by 3, and second let us call that mu2, refractive index is our 5 by 3. And the focal length, that is our f, and that focal length is, you can say, in the air. Focal length in air, and refractive index of air, in that case that will be medium, is equal to 1. And f1 is our focal length in medium mu1, and we have of f2, that is focal length in the medium mu2. And we can write that the focal length, because the radius of curvature will be, you can say, common term for all these three because length is same. So we can just for the time being can ignore this part and concentrate only on the refractive index part. So therefore we can write that our 1 upon f is proportional to, for first part, that focal length is our f, and the length is given by 3 by 2 and we have air of 1. So this comes as 3 by 2, air medium is 1, and this gives as our 1 by 2. Similarly, we can write for our mu1, that is f1, and that is our 3 by 2 divided by 4 by 3 and minus 1. Okay, here it will be proportionality. And this comes as 1 by 8. Similarly, we can write our f2 will be proportional to 3 by 2, 5 by 3 minus 1, and this comes as minus 1 upon 10. Now we can simply take the ratio and find out the relationship. So we get 1 upon f1 divided by 1 upon f. So this comes as 1 by 8 divided by 1 by 2. This will be giving us 1 by 4. Thus we get that our f1 is equal to 4 times our f. Similarly, for the second one, we can write that 1 upon f2, 1 upon f will be equal to minus 1 upon 10, and this is our 1 upon 2. This comes as minus 1 upon 5, giving us f2 is equal to minus 5 times f. Okay. And if we want to make a comparison, that is in terms of they are greater than less than, so we can also draw it, and that we can make a comparison with respect to the refractive indexes. So we have two refractive indexes. So we have mu1, that is our mu medium. First one is our 4 by 3. So therefore we can write that mu length upon mu medium, their ratio will be equal to 3 by 2 divided by 4 by 3, which comes as 9 by 8, and that will be greater than 1. Okay. And based on this, we can say that our f1 is greater than f. And for medium second part, your mu medium is given as 5 by 3. So once again we can write that our mu length upon mu medium will be equal to, this is 3 by 2 and divided by 5 by 3, giving us 9 by 10, which is our less than 1. Okay. And this is going to, okay, in the first case it behaves like a converging. And in the second case it is going to behave like a diverging. So therefore we can say that our f2 will be less than 0. Okay. And so we can combine these two options and format a result that our f1 is greater than f and f2 becomes negative. So therefore the option number B is the correct option. Option B is correct. The next question, it was asked in the 2014 mains, and it states that two beams A and B of plane polarized light with mutually perpendicular planes of polarization are seen through a polaroid. From the position when the beam A has maximum intensity and beam B has zero intensity, a rotation of polaroid through 30° makes the two beams appear equally bright. If the initial intensity of two beams are IA and IB respectively, then the ratio of IA and IB equals to. So in this case, we have you can say, two beams and both are mutually perpendicular plane of polarization. So we can draw an approximate figure, and initially we can say that this is the first one and this is the second one. So this, let us suppose, is our IA and this is our IB, and the plane of polarization is such that the A has a maximum intensity. So we can draw the plane of polarization with this dotted line. And for the simplicity, let us further represent this you can say plane of polarization by using a circle, because it will help us in, you can say, when we are going to rotate it. This is our transmission axis, and this is our initial condition. And finally, we have that both beams are equally bright. So we are going to rotate our, you can say, transmission axis, and it will be coming something like this. So the transmission axis is now like this, so that both beams, you can say, are equally. So this is our IB and this is our IA, and this is our final position. And it is said that we are rotation of 30°. Okay, so the beam is rotated through angle of, sorry, not beam but polarized axis is rotated through the 30°. Okay. So we are given that we have two mutually perpendicular polarized beams. A and B. Okay, and it is said that the intensity of A, so A is having an intensity of IA and B is having an intensity of our IB. Okay. And initially it is said that the polaroid is aligned to beam A. So because of this, A has maximum intensity and B has zero intensity. And if we rotate the polaroid by 30°, both appears equally bright. So we have polaroid rotated by 30 degree. So in this case, A and B are both equally bright. Sorry, they are equally bright. And we know the standard formula that the intensity, if it's I, of a plane polarized light of a passing through the polaroid, that is given as I is equal to I naught cos square of theta. So we know the intensity of plane polarized light after passing through polaroid. Polaroid, it is given as I is equal to I naught cos square theta, where I naught is the initial intensity and theta is the angle between light's polarization and polaroid axis. Angle between light's polarization and polaroid axis. So we can say write this formula according to initial condition as well as final condition. So initially we are given that A is aligned with polaroid, so which basically means that theta is equal to 0. Therefore we get the intensity, let us suppose that as our IA prime will be equal to IA and our IB prime will be equal to 0. And finally we are given that rotating polaroid by 30 degree. Rotating polaroid by 30 degree. So we get that for IA prime will be equal to IA cos square 30, which comes as IA 3/4, and for IB prime that will be coming as IB cos square 60, and that will be coming as IB of 1/4, and it is given that both appears equally bright. Both appears equally bright. Therefore we get that 3/4 times IA is equal to 1/4 times IB. So this gives us that IA upon IB is equal to 1/3. So the option number D is the correct one. Option D is correct. The next question, it was asked in the 2014 advance, and it states that a transparent thin film of uniform thickness and refractive index N1 is equal to 1.4 is coated on a convex spherical surface of radius r at one end of a long solid cylinder of refractive index N2 1.5 as shown in the figure. Rays of light parallel to the axis of cylinder transversing through the film from air to glass get focused at distance f1 from the film, while the rays of light traversing from glass to air get focused at a distance of f2 from the film. Then we have to find out what will be the relationship between our f1 and r as well as f2 and r. So in this case, we are given that we have a transparent film refractive index N1 1.4 and a solid glass which is having a refractive index N2 that is 1.5. And in this case we have two cases. Light comes from air to the film and then it goes to the glass, focuses at f1 after entering the glass. And then the reverse, light comes from the glass, then film and then air, and then get focused at f2 after exiting to the air. So these are two cases. So first one, we are given that there is a thin film whose refractive index is given as N1, that is equal to 1.4, and then we have a glass whose refractive index is N2 and is given as 1.5. And along it, we have two cases. And in case number 1, we have that light comes from air, then goes to the film, and then goes to the glass, and we get the focus at f1. Focus at f1. And in the second case, we have light comes from glass and then film and then come to the air, and now it focuses at f2. And we are given that radius of curvature is given as r. And we know the standard formula is that our N2 upon F is equal to N2 minus N1 and divided by R. And R is our greater than 0 for the convex surface. And here the N1 is our incident side and N2 is our transmitted side. N1 is our incident and N2 is our transmitted, and the object is at infinity. That is, as it is given a parallel rays. This is for parallel rays, which means object is at infinity. So let us sort it out for case 1. case 1, we are given that the incident medium, that is our, you can say it is air, film and glass. One second. Yeah, air, film and glass. So we have air, then it goes to the film, and then it goes to the glass. So we can write that our N2 upon F1 is equal to N2 minus 1 divided by R. N2 is our refracted medium, that is 1.5 divided by F1 is equal to 1.5 minus 1 and divided by R. So this gives us that our F1 is equal to 3 times R. And we have case 2, which gives us glass, film and air. Case 2, we have glass, film and then we are having air. So N2 is a refractive medium, that is 1 upon our F2. This is 1 minus 1.5 divided by R, and this is quite simple, that our F2 will be equal to minus 2 upon R. And in the option we are only interested in magnitude, so we can say our F2 is equal to twice of R, because they have used a modulus part. Okay. So F1 we have 3R, so option number A is the correct, and F2 is equal to 2 of R, so option C is correct. So we have option A and C are correct. Come next question. It was asked in the year 2014 advance, and it states that a bright source which emits two wavelengths lambda 1 400 nanometer and lambda 2 600 nanometer is used in Young's double slit experiment if the recorded fringe width for, it has to be lambda 1 and lambda 2 are beta 1 and beta 2, and the number of fringes for them within a distance y on one side of the central maxima are m1 and m2 respectively. Then we have to find out the relationship between the beta 2 beta 1 m1 m2 and the angular separation, along with how the central maxima, third maxima for lambda 2 overlaps with the fifth maximum of lambda 2. So we start with this basic formula, that is our beta is equal to lambda capital D divided by small d. Okay. And we are given a wavelength, that is lambda 2, and lambda 2 is our 600 nanometer. So obviously it is greater than lambda 1, which is given as 400 nanometer. So therefore we can say that our beta 2 lambda 2 corresponds to beta 2 and lambda 1 corresponds to beta 1. Okay. So therefore you can say that beta 1 is greater than beta 2. So option number A is correct. That was quite straightforward. Option A is correct. Next, we have to find out the number of fringes in a fixed distance, that is our y. Okay. And for that, we also know that our m is equal to y upon beta, and we just found out that our beta 2 is greater than our beta 1. So beta 2 corresponds to our m2 and beta 1 corresponds to m1. So therefore we can say, because there is inverse relationship, so m1 will be greater than our m2. So option number B is also correct. B is correct. Now we are going to find out the fringe width position. Okay. And it said that they are going to overlap. Okay. And in the question it is specifically mentioned that the third maxima of lambda 2 overlaps with the fifth minima of lambda 1. So this becomes quite easy from the option itself. Okay. So we have our lambda 1, that is our 400 nanometer, and we have our lambda 2, that is our 600 nanometer, and we are given that we have a third bright fringe, and we are having the fifth dark. Okay, so this is given to us, and we know the formula that for, let us suppose, that is given as y bright will be equal to m lambda d by small d, and we have y dark will be equal to n plus 1 by 2, and this is our lambda d by small d. And we are given that the third bright is equal to fifth dark. So we can say that third bright, this gives us that the value of m is equal to 3, and we can say that y will be equal to 3, and this is 600 capital D divided by small d, and we have fifth dark, which gives us that the value of n is equal to 4. So this gives us the y is equal to 4 plus 1 divided by 2 and multiply by 400 capital D divided by small d, and they are equal. Therefore we can write, or we can say we are given that the third bright is equal to fifth dark. So we can equate them. We get this as 3 into 600 capital D small d is equal to, this becomes as 5 by 2, and 9 by 2, and this is 400 capital D and small d. So this d and d cancels out, and this comes as 200. So we get this as our 1800 is equal to our 1800. Okay. So this condition is also true. It means option C is also correct. C is correct. And for the last option, we have an angular separation. Angular separation, which is a theta, and theta is equal to lambda d upon d. And once again, we are given that our lambda 2 is greater than lambda 1. So we can say from here that theta 2 is greater than theta 1. Okay. But the option that is given to us, that theta 1 is greater than theta 2. So this option is incorrect. So option C was also correct. So option D is incorrect. I think this was the last one. Yeah, so these were the all the questions that was asked in the year 2014, mains as well as advance. Thank you.